Good afternoon. My name is Nasri Munfah. I am a Senior Vice President and the Tunnel Practice Leader of AECON. Thank you very much for inviting me to your conference, and I will present to you a lecture about innovations in conventional tunneling. In today's presentation, I will be talking to you about the International Tunneling Association Working Group 19, which is conventional tunneling, its mission and activities. I will be presenting to you the background and principles of conventional tunneling, prototypical configuration of the tunnel cross-sections, application of conventional tunneling, and recent development of conventional tunneling, including the development of ground classification and support systems, ground improvement, as well as instrumentation and monitoring of conventional tunneling. In that, we also take into consideration the construction aspects, and we will discuss risk management. Then I will present to you a case history using construction station in San Francisco using conventional tunneling. Conventional tunneling is the terminology adopted by the ITA. It refers in different part of the world differently, such as the New Austrian Tunneling Method or NATM in Europe and part of Asia, Sequential Excavation Method or SEM in North America, or Sprayed Concrete Lining in the UK. Working Group 19 consisting of about 30 people, and I lead that group. Our mission is to promote the advancement of the conventional tunneling and the latest development of application of conventional tunneling. We have produced several reports which are published and available through the ITA website, and we are presently working on a report entitled Guidelines for the Design and Construction of Conventional Tunneling in Urban Areas. This will be issued next year in 2021. Conventional tunneling is a concept that is based on the understanding of the interaction between the ground and the structure itself by creation of the tunnel opening and the ground support while attempting to mobilize the optimum ground self-supporting capabilities. It involves ground engineering science, geotechnical engineering, as well as practical experience. It was developed in its present form in Austria in the 1960s for rock tunnels, then adapted for soft ground since 1968 in Germany. Presently, it is being used widely throughout the world. The principle of conventional tunneling is to allow the ground to self-support itself. In the graph on the right-hand side, the stresses versus deformation curves, it will show that the optimal point, point A, is at such a point that will be the displacement is sufficient enough to mobilize the ground self-supporting capabilities, yet the stresses are not too high. If we limit the deformation significantly, and that is moving the curve to the left, the stresses will be too high in the liner. If we move it all the way to the right, excessive deformation, then we will have a potential failure. Therefore, it's very important to recognize and mobilize the self-supporting capabilities of the ground itself. That's by recognizing the ground characteristics and behavior to the excavation and defining the ground response classes to meet the characteristic of the ground, such as adjustment in terms of the ground length, which is the maximum unsupported length, the type of support measures needed, such as shotcrete lining and ground reinforcement, or subdividing the heading into multiple drift to reduce the cross-sectional area, as well as ring closure in order to create a curvilinear structure. In all of that, we address risk management in the design to be able to address the conditions of the ground itself. The rock mass classification and support system were used initially to develop the support system for the conventional tunneling. Various systems such as the RMR, the Q, the GSI were used. However, in 2001, Austria developed its behavior-based rock mass classification and support system. What you will see on the right-hand side is an excerpt from the guidelines. It addressed the rock mass behavior and the type of support that is anticipated. This is a typical cross-section of conventional tunneling. As you can see, it is always curvilinear in configuration, and depend on the size of the cross-section, it could be subdivided into top heading and bench, or top heading, bench and invert, or it could be multiple drift as shown in the picture on the right hand side. And this is a prototypical longitudinal excavation and support classes system. What you'll see on the top is the excavation sequencing with the top heading bench and the support system, the length of the top heading and the length of the bench. And what you see in the bottom is, as it crosses the various geological profile, it is showing the type of support that is needed in various classes, such as class 1, 2, 3, and 4, depend on the condition of the ground and identifying that by stationing. In this example, we're showing also that the design approach addressing the rock mass classification and the support category. As you can see here from this graph, this is a rock tunnel in which it passes through multiple faults and with different formation throughout the length of the tunnel. So we provide the geological model, the geotechnical model, which is the ground response classes, as well as the tunnel support model, which is the excavation and support classes. All of these are shown graphically in the presentation here. One of the challenges of conventional tunneling in hard rock is squeezing ground. In order to accommodate the deformation of the ground and without impacting the structural system, flexible support can be provided, such as using steel yielding element to accommodate deformation and allowing radial displacement in a controlled manner. As you can see in the upper picture, these are steel yielding element, which are hydraulic jacks in a sense, are placed within the liner, and we see in the lower picture how they are in a deformed state. This will allow the deformation of the rock, and it is a preventive measure and prevent the failure of the shotcrete. Similar to the rock application of conventional tunneling in soft ground also rely on the ground behavior to the creation of underground opening and on its self-supporting capabilities. The curvilinear shape promotes smooth stress redistribution and minimizing stress concentration on the liner. The shotcrete provides an interlocking to the ground in order to improve the ground capabilities of self-supporting. Ground length, subdivision, and timing of the support installation are more important factors. In addition to that, in soft ground, sometimes we have to use ground improvement and pre-support measure to enhance the ground capabilities of self-supporting. In all of these aspects, monitoring of the deformation of the tunnel is very, very critical in order to assure its stability. To emphasize, the principles of conventional tunneling in soft ground is sequentially excavated, the curvilinear shapes, no corner, the initial support using shotcrete in combination of either steel fiber or welded wire fabric, lattice girder, and ground reinforcement if needed. Pre-support such as spiles, pipe umbrella, jig routing, as well as face support if needed. It's very important to close the ring promptly in order to create a complete curvilinear. It's very important that the initial supports are applied immediately upon the excavation and before proceeding to the next round. In order to accommodate that, several methods were developed, including the development of ground classification and excavation support classes. The excavation support classes address the ground behavior for the excavation by adjusting the round length, the initial support measure, and the sequence of the excavation. As you can see from the graph below, This is an example from the excavation support classes that were developed by the Federal Highway Administration in the United States. It's intended to be as guidelines rather than direct application. It has to be addressed on a project-by-project basis and a condition-by-condition basis. The excavation support classes define also means of any additional support or local measure that is needed to augment the initial support as being identified. Sequentially excavating obviously depends on the cross-sectional area of the tunnel. In the upper pictures, you can see that it is a smaller tunnel size and as such a top heading and bench in a sense to sequence, and they are not too far apart. In addition to that, pre-support were installed as well as face support as needed if needed. On the lower picture, it shows that the cross-section is much bigger. As a result of that, a top heading, a bench, and an invert were done in sequencing. As you can see from the top heading, is the ground length is much smaller than the bench and the invert, and the top heading as well as the bench and the invert, the face support was provided with shotcrete. In addition to that, there is a pre-support measure such as jet grouting or pipe arch canopy. The main support element of conventional tunneling are obviously the cross-section itself and the sequence of the excavation, and the angular support, which consisting of rock bolt in rock and shotcrete or lattice girder in soft ground, as well as a steel fiber or welded wire mesh in the shotcrete. In addition to that, ground reinforcement and pre-support. Often, especially in poor ground, we use pre-support elements such as a pipe umbrella, spiles of horizontal jet grouting, and sometimes as needed we use face support to control the face. For structural analysis and design, it's very important to take the ground and the structure interaction model and relying on the stress redistribution and the deformation of the ground, surrounding ground. Therefore, either finite element models or finite difference model will be used. Most of the time, 2D analysis is sufficient. However, at certain locations such as junctions, intersections, cavern, or difficult ground condition, 3D modeling would be important. In all cases, it is important to avoid embedded frame modeling because it does not take into consideration the ground behavior or the ground structural interaction. The excavation method depends on the quality of the ground that we are encountering. For example, in hard rock, we will use drill and blast. However, in medium to highly jointed rock, we can use rod header. And in soil-like rock, we can use backhoes. And similarly, for soft ground, we can use backhoes or other excavator to excavate the ground. In addition to the excavation and support classes that is defined earlier, we also developed what is called conventional tunneling toolboxes. In that, I will discuss some of those right now. For example, we can use pre-support elements such as spiles, grouted pipe umbrella, vacuum dewatering, or horizontal jet grouting. All of that in order to improve the stand-up time of the ground. Other measures include the geometry and the sequencing of the excavation by subdividing the cross-section into various components which are small enough. Again, the purpose of that is to limit the deformation and to tailor the sequencing of the excavation to the ground condition and its behavior during excavation. Other measures include the face support element, such as using earth wedge to stabilize the face, using shotcreting on the face, or installation of fiberglass bolt in the face. As you can see in the lower right hand picture, is showing the installation of the fiberglass face bolt, while on the lower left picture it's showing the earth wedge that is kept in place to minimize the face deformation. Other tools in the toolbox include the annular support element by increasing the length and or the spacing of the ground support, increasing the thickness of the arch shotcrete, installing temporary shotcrete in the invert if needed. All of this, the goal of this is to create a ground arch to mobilize the inherent strengths of the ground. To increase the ground capability of its self-supporting, sometimes we end up having to do ground improvement and remedial measure. Some of the ground improvement include dewatering, either a general area of dewatering or vacuum dewatering from within the excavation, permeation grouting, chemical grouting, or jet grouting, either vertical or horizontal. In addition to that, we can use freezing, which we have used it on some projects, and to accommodate the potential settlement as a result of the excavation, compensation grouting can be used to restore the surface. These are examples of ground improvement using ground freezing. For example, on the picture on the left, which is in Boston, the tunnel had to pass under existing warehouses that are being used with a very shallow cover. To stabilize the ground, we utilize vertical ground freezing from within the basement of the warehouse itself. The picture on the right is showing a crossing under Northern Boulevard in New York City, in which ground freezing was implemented to stabilize the ground because the tunnel was immediately under an existing another transit tunnel. In this case, horizontal freezing was used. It is very important to have a robust instrumentation and monitoring program. We need to monitor the excavation itself by convergence point or total stationing, the ground itself outside the excavation by multi-point settlement monitoring system, surface settlement point, and multi-point borehole extensometer. In addition, we need to monitor the adjoining facilities using systems such as total stationing or liquid level. In areas where adjoining structures are sensitive to deformation or displacement, compensation grouting is often used, and that is installation of tuba manchette under the foundation of the buildings, and as the potential settlement started to happen, injecting grout to restore the building back to its original foundation level. For successful application of conventional tunneling, risk management by design is essential. Early on through the design process, we identify the potential risk, their probability of occurrence, and their consequences, and they are documented in the risk registry. Preventive and corrective measures to either reduce the risk or eliminate the risk are developed during the design. One of the tools of risk management is the application of geotechnical baseline report, in which the ground behavior to the excavation is defined and documented. Another element for a successful application of conventional tunneling is to have progressive contractual provision. For example, contractors should be pre-qualified. Experienced personnel should be available and implemented in every shift. Flexible design document and adjustment in the field should be available. One of the tools that we have identified and implemented is the excavation and support meetings in the field, in which representative of the contractor, the designer, and the owner meet in the field every day after the work hours to assess the ground behavior and the ground performance of the excavation and determine the course of action for the following day and whether any corrective action need to be made. With flexibility and progressive contractual framework, we'll be able to successfully apply conventional tunneling. I would like to present to you now a case history, which is the construction of the Chinatown station in San Francisco in the United States. The owner is the San Francisco Municipal Transportation Agency. The Chinatown station is a metro station. It's excavated as a mine cavern in a very densely populated area. The cavern width is 16.7 meter with a height of 13.1 meter and a length of 192 meter. As a result, the excavation is very large in cross section. It is located in a dense area and a very difficult ground condition. Pre-support measures including double pipe arch canopy, spiles, and J grouting were used, as well as compensation grouting was used. Chinatown Station in San Francisco is located in one of the densest concentration of people in San Francisco. It is a highly developed urban area with historical and sensitive buildings surrounding it. It is a congested neighborhood and heavy traffic on the surface, as well as it has numerous old utilities underground adjoining to the station location. As you can see in this figure, the Chinatown station is located in a very complex and difficult ground condition. It is in a mixed ground condition consisting of soils at the upper layers and rock in the lower layer. The soil is a colma formation consisting of dense sand and silty sand interbedded with steep clay and sandy silty clay, while the rock formation is the Franciscan complex bedrock, which is variable in composition, degree of fracturing, strength, hardness, and weathering. The rock mass is extensively sheared and chaotic, heterogeneous mixture of small to large masses of different rock type consisting of sandstone, shale, siltstone, and various metamorphic rock. The RQD of this rock was consistently 0. To construct the station, we excavated the head house shaft off the street, and then from there we excavated a cross-cut cavern across the street, and that was used as a mining cavern to excavate to the north and to the south to build the station platform cavern as well as the crossover cavern as shown in this figure. Some of the challenges that we encountered are the large excavation size in difficult ground conditions. Therefore, we opted to have a prescriptive sequential excavation design. The excavation was done in small drift. Pre-support measure such as pipe arch canopy were done ahead of the face, and closely spaced lattice curtain and shock grade were implemented. We controlled the groundwater by dewatering of the area, and we provided the toolbox for support as needed if there are any changes. Other challenges included the high groundwater table. Therefore, we opted to do a pre-excavation dewatering using deep well system, as well as we provided a vacuum well dewatering from within the excavation. Another challenge we encountered is the shallow cover and the potential damage to adjoining structures. As I mentioned earlier, there are significant number of utilities in the street, as well as there are historical and sensitive buildings nearby. So, as a result, we lowered the station to increase the cover. However, we could not lower it significantly to impact its operation. We did pre- and post-construction condition survey of the building, and we applied systematic pre-support measures to minimize settlement using small drifts, and we did monitor the ground deformation during the excavation, as well as we did extensive instrumentation and monitoring of the buildings and utilities. To address potential settlement, we implemented compensation grouting program to mitigate the measures of the key structures. As a matter of fact, one of the buildings across the street, which was very sensitive for potential settlement, we had to implement compensation grouting to restore it. The maximum settlement that occurred throughout the entire excavation was limited to 12 millimeter. These are some photographs of the construction. As you can see in the upper left hand is the application of the pre-support measure using pipe arch canopy for the cross cut. The picture on the right hand side is the platform station excavation, and you can see it was done with two side drifts and the center drift top, middle and bottom. And the bottom picture shows the connection between the crosscut and the platform cover. It is anticipated that the station will be operational in the summer of 2021. What you see here are the rendering of the station in its final configuration. At the present time, all civil work has been completed and the station is being outfitted with the electrical and mechanical system and the vertical circulation element. When completed, what you will see on the upper left picture is the rendering of the entrance, then the mezzanine, which is the crosscut, as you can see it on the right picture, and the bottom picture showing the station platform and in its final configuration. There are numerous advantages of conventional tunneling. It is flexible in geometry and can accommodate almost any size or shape of opening. Its curvilinear shape promotes smooth stress redistribution in the ground, minimizing the need of heavy structural system. It is adaptable and can support allow tunneling through a variety of ground. No special equipment are required, and the tunnel cross-section, if it is big, can be subdivided into multiple drifts to provide stability of the excavation and minimize the impact on the ground. Shotcrete is a key support element due to its capability to provide an interlocking with the ground, provide initial support, and continuous support to the ground. Implementation of ground improvement measures such as dewatering, grouting, ground freezing, or other measures enhance the applicability of conventional tunneling in various ground and in more difficult areas and in urban areas. It is essential to have monitoring and to verify the design assumption and for adjustment of the tunneling process during construction. It's important to have progressive contractual requirement and rigorous risk management for its success. It is a flexible and adaptable tunneling system suitable in all ground and can accommodate almost any shape and condition. I thank you for the opportunity to present to you advancement in conventional tunneling, and I'm available to answer your questions.